Welcome to qnawire.
So here we have a diagram of our situation in phases. Initially, the cylinder A is at rest, so there is no linear momentum of the cylinder or the cart. Then, when the cylinder is released from its rest position, there's an impulse due to its weight acting on the cart, which is WA times T, where WA is the weight of the ball, and an impulse acting upwards on the ball of WB times time T. The final state of motion includes a linear momentum of the cart to the left of MB/VB, where VB is the velocity of the cart. The linear momentum of the cylinder at point C is MA/VA, and the cylinder also has angular momentum I omega, where I is its mass moment of inertia. So we can get from here that with a bit of kinematics, that Vb, the speed of ball B as it moves, or the speed of the cart moving to the left, is equal to Vc at point C, and this is equal to R omega minus V bar A. So there's two contributions to the cylinder's motion. So that due to its angular motion and its linear motion. And so from here we can see that the angular speed at which the cylinder is rotating, omega, is equal to the linear velocity of its center, V bar A, plus Vb, the velocity of the wooden cart, over R, where R is the radius of the cylinder. So the round cylinder has radius R. Now, using our diagram and taking the principle of impulse and momentum, we can look at just the horizontal components or the x components. We can ignore the y components. And since there's no forces in the x direction, we know that the x components must be conserved. So the initial momentum of the system is 0. And the final momentum, or the x components of the final momentum, is ma v bar a minus mb vb. And this must equal to 0, the initial momentum of the system. So substituting our values in here, we get that 6 pounds over g, the mass of A, times the linear velocity of its center, VA, is equal to the mass of B. The wooden cart has mass, weight 10 pounds, over g times its velocity, VB. And then from here we can see that VB, the velocity of the track, is related to the linear velocity of the center of the cylinder, VA. VB is equal to 0.6 times VA. So now we have an expression that relates the two speeds, speed of the cart and the linear speed of the cylinder. So now let's look at work and energy. So firstly, the work done in going from state 1 to state 2, we'll call it U, is equal to the weight of ball A times the distance, which is 6 inches. So 6 inches, remember, is the height from its highest point to point C. So that distance, vertical distance, is 6 inches. So the work done is the weight times the distance 6 inches. So this is a weight of 6 pounds, and 6 inches is 6 by 12 feet. And so we get the work done to be 3 foot-pounds. The initial kinetic energy, T1, is equal to 0. The entire system is at rest. So now we'll calculate kinetic energy. We've done the work. We'll calculate kinetic energies. T1 is equal to 0. T2, in the second state, is equal to a half ma va squared plus a half I omega squared, that's the angular contribution from the cylinder, plus the linear contribution of the cart, a half mb vb squared. We know that vb is equal to 0.6 va. We've already calculated this. And omega is, from above, we calculated omega to be va plus vb over r. So we can simplify omega. So omega is equal to va plus vb over r, which is 1.6 va over r. So it's va plus 0.6 va over r. So we can then write T2 in terms of VA. So T2 becomes a half into 6 pounds over G V bar A squared plus a half into a half times 6 over G times R squared multiplied by 1.6 VA over R all squared plus a half times 10 over G times 0.6 VA squared. And so this simplifies to 3 over G VA squared plus 3.84 over G VA squared plus 1.8 over G times again VA squared, and hence we get the kinetic energy of the system in state 2 in terms of VA to be 8.64 over G times VA squared. G is just the gravitational acceleration. So the conservation of work and energy tells us the following. So the energy from state 1 is conserved with state 2. So the initial kinetic energy plus the work done on the system from state 1 to state 2 must equal to the final kinetic energy at point C. So 0 plus 3 foot-pounds must equal to 0.64 over g, which is 32.2 feet per square second, times VA squared. And hence we get VA to be 11.181. VA squared is 11.181, and so VA is equal to, so vector VA is equal to 3.344 feet per second, and that's the velocity of the cylinder, and that's to the right. And therefore, we can calculate the speed of the wooden cart. So VB is 0.6 times VA, and that's equal to 0.6 times 3.344, and therefore we get that the velocity of the wooden cart is 2.01 feet per second, and that's to the left.